So this guy here, does anyone need this guy? Yes? Okay.
Thank you.
You need it? Okay. That would mean I will have given away more than I should have to people. Okay. This is mine. Hold on, let me turn this off. I've only got one copy left and I need it. Sorry. I printed out more than I have people, so I'm not sure which is happening. If you need a copy of this, obviously you can see me after class or something, right? So this is, it's got the 12.1, 12.3 summary stuff. We did some example problems at the bottom. We're about to finish up 12.4 and get into 12.5, so we're going to get back to this in a minute, but I just want to make sure you guys have it. At the moment, some stuff on here might not make sense. That's fine, we haven't talked about it yet. What we did do last time, I think we ended up here. And I'm going to pretend like you guys can read all that, but it's insane. This was our attempt. This is the cross product. And one immediate thing you see that's different from the dot product. What kind of answer does the dot product give us? Can you describe it? Scalar. And cross product gives us a vector. Can somebody? All right, and we did this last time, and you can see how I told you what was going to happen. How did we develop this answer? We developed this answer by assuming the answer for a vector that was perpendicular to two given vectors and solving. And we didn't do it all the way, I don't think. We didn't want to do all that algebra, but that's what you would get to, yes? So you can, if you want to, memorize that beast. But let me give you another way to look at this. And I need to review something that some of you guys might never have done, which is going to come up again later. And if you're in my 284, it's going to come up in a big way. So let's review something called determinants. Has anyone ever heard of determinant of a matrix? Yes? Okay. One person. Okay. So here we go. So if I have a matrix, let's make a little tiny one. 1, 2, -3, 2. Sure. The determinant of it, you see how that looks like absolute value symbols? Which makes me think of length or magnitude or something, but okay. At the moment, that's just the symbols we use for this process. So here's how a determinant works. So in linear algebra, it rules most of the class. We're going to see. In this class, we're going to use it just for a minute, and we're actually only going to use it as a way to get the cross product faster, instead of memorizing that and same thing. So I think one person said they know how to do the determinant. I don't know if I want to put you on the spot. How would you figure out this guy's determinant? Yeah, so it'll be 2 times 1 minus -3 times 2. So then you get 2 plus 6, you get 8. That's crazy sauce. So just to show you kind of like what a determinant might be used for other than what we're about to use it for. Can somebody tell me anything special about this matrix here? All right. Yeah, that's more like our linear algebra notation. So, do you see how row 1 is half row 2, or row 2 is twice row 1? Column 1 is twice is 1/2 column 2. Or, you guys with me? So there's a terminology called linearly independent. So one row is one column or one row is dependent on the other one. You guys with me? What is the determinant? 0. And if this was part of a system of equations, right? Would there be an issue? See, this would give me infinite answers because this is actually the exact same information, yes? This would give me no answers. So it seems that the determinant being 0 is bad. Or good, depending on what you're looking for. It's a special case. Yes? Okay, so a 2 by 2 determinant is very straightforward. I'm desperately going to get us to a shortcut, but I do want to give you a slight idea of how this full thing works. So what if I had a full 3 by 3 dude? Okay. I want to figure out his determinant. Now listen, I'm not going to prove to you why this is true. It's not the point. I'm going to show you how this would be done and then give you a shortcut, thank the gods. What do I do? And this is tricky. You can check me if you don't believe me. You can pick any row or column you want to. I'm just going to pick the first row. And what I'm going to do is I'm going to take 1 times the determinant of everything that is not in the row or column of that 1. What would that be? 1, 3, 2, 4, yes? And this is awesome. It just get more and more complex. You ready? So then I'm going to do minus 2 times everything that is not in its row and column. What would that be? 4, 3, negative 1, 4. Yeah, I got you. And then I would do plus negative 1 times all the... Okay. And so if I had an even bigger matrix, I would break it down the same way. I would have I'd have several 3 by 3s, and then I break them down this way. I can always break it down to 2 by 2s. And 2 by 2s are beautiful. No, because it would be this, minus this, plus this. And it's already a negative. Okay. What's this guy's determiner? 4 minus 6. And then, so that's 2, that's crazy. And this will be minus twice. (16) minus negative 3, so 19, is that cool? 38. And then this will be minus 8 plus 1, is that cool? So that'll be negative 45? He says completely confidently? Okay. Now, if you've never seen that before, it's trippy. It's not a huge part of this class. Yes?
Wouldn't it be plus 9?
I
Because
don't
the
know.
negative 1.
No. So this is 8 minus negative 1,
Oh, okay.
right? And so, yeah, then it's minus, no, yeah. Okay. Maybe. 4 minus 6. Yeah, that would be great, Jeff. So this should be negative 49. Okay, yes. Thank you. All right. So we're not going to do a bunch of problems like that. I'm about to show you the shortcut. It's a way to get the cross product quickly without memorizing the A2, B3, blah, blah, blah. Yes? You with me? Let me do this. Let me show you the shortcut using this guy. And then I'll do an actual cross product problem. Yes? That'd be great, Jeff, if you could just do a cross product problem. So here's the shortcut. Same exact matrix. But I'm going to repeat the numbers here. Okay. So just repeat the matrix next to itself, yes? So here's what's nifty. So you have an option. You can do it with the matrix, or you can just memorize the A2B3 craziness, yes? Either way is fine with me. Every full diagonal, do you guys see how these 3 here? So let's see. This will be 1 times 1 times 4 is 4. 2 times 3 times negative 1 is minus 6. Yes? Negative 1 times 4 times 2 is negative 9. Where am I at? Oh, negative 8. Good job, Jeff. I'm having to really make sure this is right. Yeah. Negative 6, negative 8. Yes, okay. And then if I go this way, I do minus negative 1 times negative 1 is 1. 2 times 3 times 1 is 6. 4 times 4 times 2 is 32. Okay. So I'll see if I did this right. Let's see. 38, 39, 43. Maybe. So this will be negative 2 minus 8 minus 39, yes? So we get negative 49. Yeah. It's just and again, in linear, we're going to do a bit more with this.
Wait, how did you get the other thing? 1 and
This here?
Yeah.
So, this are here, minus this.
Oh, okay.
So sometimes what you see a shortcut, you don't even include this last one, because it doesn't get used. Okay. I love it. So a cross product, if I want to do, here, let's do this 2 different ways. I'm going to write this again, maybe more legibly. Here's the full-blown cross product that you can memorize if you want to, if you feel like it. Okay. That one I showed you at least the beginnings of the problem, and then I showed you how the algebra, and then you would get here eventually. And that was when we assumed the form of the answer, dotted it with 2 different vectors, equal to 0, and then we solved. I wanted a vector that was perpendicular to 2 given vectors. Okay. This is the actual thing. So let's see if you guys can go with me on this. So here's how I do a cross product of 2 given vectors. The first row is I, j, k. And then the second row is the first vector, and the third row is the other row. And the right, bless you. Bless you. So here I can just, now maybe you guys see for the shortcut I can just write those 2 columns. You guys, let me see. Do you guys see how I get A2, B3, I? Isn't that A2, B3? And if I look ahead, won't I get minus A3, B2, I? Blah, 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 blah. You guys? Okay. Yes? So even if you don't fully understand determinants, it's not a part of this class. We're not going to do a bunch of determinants, but it's just a determinant, in some ways, is a nice way to get the math I've got to do organized. Because it's a mess. Remember what we did last time? And in fact, I got tired of the algebra and just jumped to the answer. It's a mess, but this organizes it for me. And I can see all of the components. In the middle, isn't there an A3, B1? Isn't there also a minus A1, B3? Yes? If I look at the J and the J part. Okay, so let's do a concrete example. Dear God, Jeff. Let's say A is 1, negative 1, 2, and B is 2, 3, negative 1. I want to know the cross product between those. So yes?
Why did we leave out the K math?
Oh, I said up here that very often if you're going to do the shortcut, since you end up not using this, you don't have to even write it. Yeah, yes?
Why don't you use it?
Doesn't work. So, this shortcut exists because of all of the way we rewrite the determinant. It just kind of lined up beautifully. So somebody realized. So this isn't given to us by aliens and said this is how determinant works. This is somebody going, holy shit, if I just do this and do this, it's the same thing. That's how a lot of shortcuts work. It just happens to work. Yes? Just because of the way, and you can tell, how do I do determinative of 2 by 2? Isn't it this times this minus this times this? So when I do this way, it's positive, and when I do that way, it's negative. That's just capturing what we would do for each individual thing, yes? Okay. Love you guys, yes.
And you don't need to do the second, third column because you already have the k is already positive and negative.
Yes, exactly. There's a positive one, and then there's a negative one. Exactly. Good. Okay. And again, it's just a shortcut. So for us, you don't have to fully understand determinant. You don't have to know what it's used for. We just have an immediate shortcut use of it, right? So how am I going to set this up? What goes in the first row? IJK. And then, so I want A cross B. And then if you want to, you can repeat a couple things. So this is an option. You always have the option of memorizing this. Flush, flush, flush. Me, I only have so much space up here, and I think if I have to memorize anything else, I'm going to forget something like my last name or something. So I just have to be deleted to make room. So I'd rather have a process I could just use. Yeah. If you're really kind of smart about it, you can collect your I stuff. So don't I get 1I here? And then I'm going to get minus 6I here, yes? So you get negative 5I. So my I's are taken care of. You guys kind of with me? So I can shortcut the shortcut. 4J minus negative J. So that's 5J. $3K minus negative 2K. Oh, that's neat, Jeff. I didn't mean to do this. Is that right? 5K? 3K minus negative 2. Yeah. I wish I should have been like,
Yeah, I did that first.
no way. Huh? Sure. This is 1I, yes? I times negative 1 times negative 1. It's 1I. And this would be minus 6I. So I'm just kind of doing my I's, doing my J's, doing my K's. Just so I can get to the answer even quicker, so I can shortcut the shortcut. Let me stop for a minute. This is new. Please don't focus too much on the idea of determinant if you don't need it for your other classes. If you're taking linear, you probably should, you're gonna focus on it because you're gonna have to. For us, it's just a quick tool. And I didn't have to explain. I could have just said, do this shit, but I wanted you to see why it kind of works. Okay. What do you think would happen if I did B cross A? Well, let's try it. Set up B cross A. So this one we got negative 5, 5, 5. Let's do B cross A. Set it up. Oh, wait. No, Jeff, you don't put the thing over the thing. Okay. I guess I won't wait. I'll go ahead and do it. Oh, 2, 3, 1. Do you see how you can see very quickly? You'll get 6I minus I. You get positive 5I. Yes. 6I minus I. I lost an eyeball. It's terrible. And then negative J minus 4J. And then minus 2K, where am I at? Yeah, minus 2K, minus 3K. How does that relate to, how does B cross A relate to A cross B? Yes. Beautiful. Yeah. And very quickly, not very quickly. Do you guys remember the right-hand rule? Wrong. Okay. So the basic right-hand rule, this is X, this is Y. Which way is positive Z? So you put your in the direction of x, you curl in the direction of y, z should be pointing up. Every cross product follows the right-hand rule. Which direction will your vector be pointing depends on which order you did the vectors. So help me out. What do you think I cross j is?
Negative J cross I.
Oh, okay, I see what you mean. But I want the answer. I don't want a rewritten problem. I want the answer. I's along the what axis?
X.
X. J is along the y. So what's I cross j?
Okay.
K. Okay. Can we stop for a minute? You could prove it. Yeah. Isn't I, what's I? And what's J? So then you can do I, J, K, 1, 0, 0, 0, 1, 0, I, J, 1, 0, 0, 1, and you'll get no I's, no J's, 1 K, no K's, no I's, no J's. Yes? And it works, and it makes sense, because X cross Y is in the Z direction. They're both unit vectors, so any multiplication I do should preserve that one length. Let me stop for a minute. Yes? Oh, you're good. Okay. Just wait a minute. Okay. So here's a cool little thing. So somebody help me out then. What is J cross I? Negative K. I like it. So if you put your palm in the Y direction and then curl towards the X, the only way I can do that with sort of work is if I put my thumb down. So the Z would be pointing down. That would be negative J. I mean, negative K. So here's one little cool thing I learned from my stint in engineering version of electromagnetics, which was exciting. A little circle you can make. I, J, K. I cross J is K. J cross K is I. K cross I is J. And if you go backwards, you get negative. Is that kind of cool? J cross I is negative K, so if you go backwards, you get negative. If you go forwards, you get positive. Just a little quick way to deal with IJK cross products. Okay. Yes?
That method matters. How does the length of the cross product depend on the vectors we're doing?
Oh, here's, all right. It's almost like a planet view. Okay. This is exactly where we're going next. Is everybody semi-cool with this? So the direct result of a cross product is a vector. What's true about that vector compared to the vectors you put into the cross product? The resultant vector will have to be how related? Perpendicular to both. Cool. Can this work then strictly in 2D? No. It's a 3D thing. There are analogs to cross products in higher dimensions, but the direct cross product lives only in 3D. Can't even work in 2D because you would have two things and they have nowhere to exist, the result. Does that make sense? Okay. So, remind me, dot product, can you guys remember what I wanted the dot product to accomplish? So we had an example of like something here and then something here. This had a length of 2, this had a length of 3. What did I want the dot product to do? I wanted it to be multiplication, but since the 2 and the 3 don't agree, if they did agree, it would be 6.
It's like shining a light down on it.
Yes, so I want the shadow of 2 that lies in the direction of 3, I would multiply that with 3, correct? And that's where we come up with the length of A, the length of B, cosine theta. Because what is the shadow of 2 along 3 if this is theta? What's this? 2 cosine theta, yes? So our dot product can be seen as, yeah, there, cosine. You're coming. This. Now, what I want to do is, did I already show you? Let me see if you guys remember. I did this with you. I did this definition with you first. And this is the way I would just do it if I just needed a dot product and I didn't know what the angle was. Screw it. I just gotta multiply the components of the vectors, add them up. Yes? Make. Okay. The fact, and then we actually took this definition and we constructed this truth. We did that together. And that, of course, gave us a way to figure out the angle between any two vectors. If I set this equal to this for any two vectors, I can solve for theta. You guys semi. And of course, that led to projection and all that kind of business, right? I want to do something similar with cross product. If the dot product is multiplying only the parts that agree with each other, the parts that are pointing in the same direction, to make a complete picture, the cross product should be multiplying only the parts that are perpendicular to each other, yes? You guys with me? So, if I have my two vectors, let me make it more general. Yeah. A and B, sure. And I want to only multiply the parts that are perpendicular to each other. So, I don't know why necessarily, because the first thing I would do is make that straight, yes? How do I get the part of A? So, and we know the angle. How do I get the part of A that is perpendicular to B? Holy shit, yes. So this would be this piece here. So this is the length of A, this is the length of B. This would be the length of A sine theta, yes? So, if I only want to multiply the pieces of the vectors that are perpendicular to each other, I would take this length times this length, yes? And what would I get? This length times this length. If I put it in little alphabetical order, I get that. Okay. Which again, I kind of told you that if I want the other way to define multiplication to give me a complete picture, and the first way had a cosine in it, the other way's got to have a freaking sine in it to make it a complete picture. So somehow, the expression we just had for the answer is going to relate to this. So here's the relationship. The length of A cross B is going to equal this. Because of course, what kind of thing is this? Is that a vector? No, it's a scalar, of course. Length times a number. So it's a length, it's a scalar. Okay, maybe. So I am, again, as long as you guys are cool, if I ever don't do enough algebra for you, you can do the steps I skipped. So I'm going to start the problem, skip a few steps, show you how you eventually get here. I'm sorry. So what I do, thought I wrote some, is I'm going to look at this. And remember, the cross product straight up definition is this, yes? So wouldn't this be this squared plus this squared plus this squared? Is that cool? Because I'm squaring it so the square root goes away. So I just get a to b3 minus a 3b2 squared plus a 3b1 minus a 1b3 squared plus a1b2, then a squared minus a to b1 squared. Yay! And then I square all that shit out. So if you want me to do all that, too bad, I ain't. If you do some algebra, So
if you write that on a test, would you accept it?
only if I ask you to prove this, and even then, it's probably bonus, so I'd give you 1 point instead of 2. I could have just said try it. Alright. Believe it or not, and you guys can maybe tease out, if I FOIL all this business out, I can collect certain things together, and then I can factor it. So believe it or not, it ends up, after a few steps, it ends up like this. So what you get right here, where is it? Like here you get a1 squared b1 squared plus a1 squared b2 squared. a1 squared b2 squared would come from right here. And this would involve some adding, subtracting the same version and so forth. So there's this step here is about 4 or 5 steps. But you eventually get here. Does anyone recognize this? Yes, the length of A squared. And of course this would then be length of B squared. Does anyone recognize this? Yes! So this would be minus the dot product, calm down Jeff, squared. Now, help me out. What's the formula for the dot product that involves theta? So this is squared, yes? Stop for a minute. What's 1 minus cosine squared? Sine squared. What's 4 minus 4 cosine squared? 4 sine squared. So what's a squared b squared minus a squared b squared cosine squared? A squared b squared sine squared. Yes? And that's equal to what I start off with, a cross b squared. So if I take the square root, I get that. Okay, maybe. Which jibes with what I want it to be. I want the cross product to be just multiply the components that are perpendicular to each other, because the dot product gets the other stuff. Yes? Yes?
So you're multiplying length A and length B by sine, which is the ratio. Doesn't that mean you're using the y of length B?
Well, if you look at this, I set it so that B was in the base. I could have set it so A was in the base. Yes?
What if neither of them is in the base?
Turn it until one is. Yes? If I have an angle between two vectors, and they give me two vectors and the angle between them, I'm allowed to set them in my coordinate system however I want to. Even if they gave me sitting in somewhere, I still could look at, because all the work I'm doing is internal to these.
How would you turn them?
The way it did. So there it was, and I went, bam.
No, but like mathematically.
Oh, okay, okay.
Like if you're given the coordinates for the
So
two
real quick,
vectors, how would
if somebody tells me points, and then I figure out the lengths, and I figure out this is a right triangle, do I need to worry about what the original coordinate system was, or can I just get the area of that triangle by doing half the base times the height? Do I have to worry about how it was oriented in the original coordinate system? No. Right? All the information I need to get the area of this is given to me by the picture. It doesn't matter how it's oriented in the original coordinate system. Yes? So the same thing here. It doesn't matter where they stuck this dude. What can I always do with the vector that's sitting somewhere? Can't I pick it up and start at 0, 0? That doesn't affect what it is? Because I can always, to be honest, what we're really doing is picking up the coordinate system and just moving the origin to a better place. But of course you can do that. Yes?
Oh, I guess I have 2 questions now. I think what you were talking about, could we just use the dot product formula to determine the angle in between those two, and then bring it to the 90 degrees using the sine or cosine? So for example, if I have some floating 2 vectors that have, like, let's say, the 128 degrees between them, and we bring them to 90 by getting this sine of, I guess, sine of 38 degrees or something like this. So to bring it down to be 90, the same thing you did with the picture.
Oh, okay,
So
sure.
we always need to bring them
So-
to the 90 degrees, correct? To do the cross product? Using this
Why?
sine theta.
Why did we make it 90 degrees? Because I wanted these to multiply the parts that were perpendicular.
Yeah.
How often are we actually going to do this Never.
Okay.
This is used to prove this expression.
Also for the cross product, they don't need to be 90. Always.
Oh, hell no.
Oh,
In fact, are these? These are just whatever angle they are.
oh, okay.
The cross product, the dot product tries to multiply the parts that are pointing in the same direction. The cross product tries to multiply the parts that are perpendicular to each other.
So what if they not?
They weren't. These
Yeah,
vectors are not.
Yeah,
These
so you
vectors
just-
are not.
you just
So
decide-
I'm saying this part of the A vector is. And how big is that part? This.
Yeah.
Okay.
So he was asking what if they are, because this is an easy solution if we have one that lays on the y-axis and then we have the one that lays on the x-axis. He was asking what if they like floating around. So my point was, can we just use the dot product to identify the angle in between those and then
Okay.
make
So if
make
you
them
want to
into-
use this to get the dot product, I need to know the angle. Yes? Now you could use the dot, you can always use the dot product to figure out the angle between the two. Always. And then you could just throw that in here to figure out the cross
Is
product.
there an easier way
Or at least the length of the cross product, yes? Is there an easy way to do what?
to identify the angle in between the two vectors floating
No.
around? Okay.
So if I have two vectors in 3 space, dot product method for finding the angle is the quickest way, unless you're lucky and they line up, like you're saying. Okay. So it's a lot like, all right, guys, here, let me ask you this. Can you guys tell me the dot product of these two vectors?
The 11?
11, yeah? Because how you do dot product? You multiply the components and add them together. So the answer to a dot product is as a scalar, yes? Did I have to worry at all about the geometry behind what this represents? Did I have to figure out an angle? Did I have to do any of that? No. If I want to figure out the angle, I could now set this equal to the length of the first one times the length of the second one times cosine theta and solve for the angle, yes? If I knew the angle, I could have found the dot product a different way. If I knew the lengths and the angle, I could figure out the dot product. Okay, and that doesn't happen very often. Okay. I feel like you're worried about something that you shouldn't need to be. One thing is the orientation in space. Well, we define how space is defined. So I can move my coordinate system however I want to. If that's the only part I care about, I can move it so that it lines up. It doesn't change the math of it at all because the math is contained. The math I did for that doesn't depend on where in fact, I didn't even draw a coordinate system. I did it relative to what I had here. Does that make sense? I feel like you're worried about something you don't need to be. And I don't blame you. Yes?
Can we see the bottom of that page?
Oh, this guy?
Okay.
Okay.
Thank you.
So I'll be really, really clear. A couple things. One thing I haven't said yet. I want you guys to see it. They're kind of cool. If I have a parallelogram, how do I find its area? Yeah, I have to figure out the height, yes? And then I just multiply that by the base. And of course, if you just pick this triangle up and put it there, you make a rectangle, and that's one way to kind of sort of prove. Yes? So if I consider this to be a vector and this to be a vector, right? And I kind of drew this horribly. I think we'll be okay. Yeah, this is fine, because this is a big S vector. I was looking at just this whole thing is a vector, yes? Okay. So it's sort of like how I would determine A plus B. Okay. So when I do A cross B and I get the length of it, I am literally getting the area of the parallelogram described by A and B. We basically did that here. What would this be of this parallelogram? This would be the height, yes? If I would have just drawn it better. That would be the height. And this would be the base. That's exactly what we did. So it's a neat little offshoot. If I have a parallelogram defined by two vectors, how do I get the area of the parallelogram? The length of the cross product. That's silly. Now let me ask you this question. What would I cross I be? Zero.
Yeah, because they're both going in the same direction. The parallelogram is a flat line.
Exactly. So if you think about it geometrically, you're going to end up with a flat line. If you think about it if you put the same vector in twice, you're going to have the same thing subtracting away. You're going to get 0 at the end. So how to make a dot product 0? The two vectors have to be perpendicular already, because who gets control over the perpendicular parts? Cross product does. So poor little dot product, if they're perpendicular, he doesn't get any of that. Poor little dude. How do I make a cross product 0?
Same direction.
If they're in the same direction, either 0 degrees or this is going to hurt 180. I can't do that shit. Yes? Here. 180. Okay. 180. Okay. You guys with me? Yes?
So, the definition of the cross product is you take two vectors, take the cross product, it gives you the third vector that is perpendicular to both of them.
Yes.
So how is taking the length of the vector gives you the area of the parallelogram in between those two vectors?
If you understood this, it immediately is just, isn't this the height? And isn't this the base?
Yeah.
So this parallelogram's area. And which parallelogram? Every parallelogram in existence. Because I just drew this it would be equal to this, which is the length of the cross product. And again, there's no reason it should be, necessarily. But it is because a consequence of how we defined it. We defined it in this way, so it's not really surprising. It's not like a magic property of nature, you know? Does that make sense? We defined the shit, so, ooh. But no, it's trippy. It's very trippy because you're all over the place and you got a lot of, obviously with this one, there's a lot of cross products happening. It's kind of a gross expression, so it doesn't feel like anything about it should be nice, but it is. Okay. Let me see. Very where I want to go next. So a few more properties. So one property we already got is A cross B. How does that relate to B cross A? We just talked about that earlier. It's the negative. Okay. A few more properties, and interest of time, I won't necessarily, but if you want me to prove, I think I will prove, I don't know, we'll see. This one is kind of like the same thing with the vector multiplier kind of dancing around in the dot product. I don't know if you guys remember that. As long as the multiplier is in there somewhere, it's the same. It doesn't care. So if I want to do 2 times 3 times 4, could I do 2 times 3 and then multiply by 4? Is that different than if I do 2 times 4 and then multiply by 3? No. So as long as the C is in there somewhere, it's going to come out the same at the end. That's what that's what property 2 says. Similar property with dot products. What do you hope this is? A cross B plus A cross C. And it is? Sorry. Are you upset? I'm sorry. Damn it, Jeff! What do you hope this is? And actually, do you see how 3 and 4 are the same? But not really. Do you see how I have to be very careful where I put the C? Yes? Why? Because is cross product multiplication, is that commutative? Property number 1 tells me it's not commutative. So I have to be very purposeful which one I put where. How do A dot B and B dot A compare? Same. They don't have that kind of problem. They like it. Okay, this is the big one. Let me put this one first. Yeah, I'm going to put this one first. A cross B cross C. Just nothing but crosses all the way down. This one's trippy. This one's not so obvious. Let me ask you a question. Is this answer going to be a vector or a scalar? Vector, because this would be a vector, and then A cross vector is vector. What's your vector? Vector, vector, vector. Okay. So believe it or not, this one comes out to be A dot C times B minus A dot B times C. It's not dotted with B. What's A dot C? What is it? It's a scalar. So scalar times B is a vector, minus scalar times Z is a vector. So vector minus vector is vector.
In the context, you're using C as a vector, not a scalar.
I like it, yeah, because it's got a little vector symbol over it. Yeah, you're right. It kind of sucks that we use, if it doesn't have a little vector symbol, it's understood to be a multiplier, because we like C for constant. But we also like C because we use A and B. So it kind of sucks. This is the big one. A dot B cross C. Can you guys tell me the answer should be what kind of thing, physically?
A number. Well, it's a, yeah, a number.
Number, because cross is a vector and then A dot vector is number. Yes? So the answer should be a number. So you would have a guess as to what this is going to be? So there's no pretty way, but I can at least do this. That is definitely not obvious. But the funny thing is, it's just playing around with shit. Some math, not all of it, but some math is just somebody. I mean, back in the day, they had candles and books,
And nothing else to do.
and not much else, especially if it was a rainy day. So what are you going to do? You're going to sit around and play with vectors.
I mean, Sir Isaac Newton developed calculus because he was he was quarantining during a plague.
There you go. So the more time you got, and the more you understand math, the more you can play around with it and create new shit. So it's kind of neat. Okay. Do you guys remember, real quick, Calc 2, you learned about sequences and series. Do you guys remember that? Wasn't that fun?
Yeah.
Okay. That actually preceded, analysis of sequences and series led to derivatives. It wasn't the other way around. But how do we teach it? You learn all about derivatives and then you use them to create series, yes? So they actually analyzed series and from that noticed a progression of the coefficients that, oh, that's something else. It's something else, and that's derivatives. So the order we teach in is not the order it was discovered. Anyway, sorry. All side note, I'm sorry. Blah, 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 blah. Oh, good, that was that. Good. Yeah, okay. All right, couple more things. We already know a couple things. I'm going to start here. A and B are parallel if and only if A cross B is 0. So we just talked about this a minute ago, but just want to make it official. Blah, 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 blah. Oh, do I want to do this? Let's see. No. No, okay. What was the other thing that lost it? Oh, and then two other things we already kind of talked about. A cross B is orthogonal to B and A. And they follow the right-hand rule. Thought there was more, but I think I already got all of it out there. Yes. So here's the thing about this little dude, that last dude I wrote. The length of A dot B cross C. First off, this is called the scalar triple product. Because math people were very creative and we said, oh, it's scalar, when the answer is going to be scalar, and there's three things in it. The scalar triple product. Remind me the length of B cross C? Isn't that in the xy plane, that would be the area of, oh my god, my poor little 3D. The area of the parallelogram described by B and C, yes? Now here's what's really neat. If I dot it with A, I end up, let me see if you guys are with me on this. No, probably not really. I'm going to spend too much time on this. B cross C, the length of that is going to be the area of the parallelogram, yes? Now, if I have a three-dimensional object, I'm going to add height in, yes? You guys with me? if the height is slanted, don't I want to use the part? All right, let me see if you guys are with me. If I dot two vectors, let me see if I can do it. Yeah, perfect. Dot my arms. I'm sorry. Cross product my vector arms. My head might be the result. Is that cool? Because my head is perpendicular to my arms. You guys with me? Okay. If I cross product these, I end up with the area of this parallelogram that these two describe. Yes? Okay. Draw another arm over here parallel to this arm. Another one there. I got a parallelogram. If I want the volume of the box that has my head, so this could be, I have to get the part of A that is going the same direction as my head. So that's why the dot product will end up doing that. So this is effectively length times width times height. B cross C is length times width, sort of, involving based on side. It has the angles in there. And when I dot it with A, that brings the height into it. So this is trippy. So I end up with a parallelogram, but in 3 dimensions. I'm not going to draw that. I can barely draw a 3-dimensional box. So it's like length times width times height, but since it's all slanted, it involves a bunch of angles, and this captures all that stuff. And what you call a 3-dimensional object that has parallelograms as sides, you call it, believe it or not, you call it a parallelepiped. Exactly, a parallelepiped. Of course. What else would you call it? And this is just a little side note. If you do this triple scalar product, bless you, and you take the length, or the absolute value, I'm sorry, in this case it's absolute value, which is why my 284 people, you know this is the real thing, but will be okay. Then you will end up with the volume of the 3-dimensional parallelogram side parallelepiped. Kind of nifty. Not the most important thing, but it's there. Okay. So let's do this. What time is it? Until what? 2:35?
Yeah.
Oof. To who? 2:30. So before we go back to that sheet, let's look at 12.5 real quick. Remind me, in 2 dimensions, what do I need to get the equation of a line? Yes, point and a direction, yes? If you give me a point to start at and a direction to go from, right? I can go. I just have to do multiples of this to get however far I want to go down the path. Yes? Yes, 12.5. 12.4 is all the cross product stuff. In 3 dimensions, if I give you a point, I also need a direction to go, but my direction has to have more information than normal. In 2D, I just have to know how far up and how far over I go. In 3D,
Up, over, and back.
yes. So there's no way to make a triple ratio. Well, let's not go there, right? So I can do y to x. I don't want to try to hold 3 pieces of information in 1 ratio. So we have to do it in a slightly different way. So let me show you a picture I could never recreate by hand. If I'm given a point and I'm given a direction vector, yes? So in 3D, it's the same idea. I could do this and I could say, so this will be like my slope in 2D, but now it's 3, so now it's going to be a direction vector. So my direction vector is at V. And for some reason they're really sticklers about it, and they're saying if I pull it up, now it's some other vector A, but that's the direction I'm going in. So if I give you a point in 3 space, there's a related vector with that, yes? So my point x naught, y naught, z naught, my vector is r naught. If I add some multiple of my direction vector, I can get another point on my line. So the form of the equation of a line in 3 space is analogous to the form in 2 space, I'm just not going to have it's just not going to be quite as easy to work with directly because I got 3 components of my direction I have to work with. So on one level, this is nice because what I do in order to get my resultant vector. So here's the idea over here. If I'm given an R naught, an initial point, I want to say, what are all my R's that actually point to points on my line? So this is my book, so I can do this, damn it. So if I say this is R, isn't R minus R naught on my line? This is R and this is R naught, this is R minus R naught here, yes? Okay, I really want you guys with me, okay? This is R naught. R minus R naught is right here, yes? The length in that mouth, yes? Okay. Isn't that a multiple of V? Didn't we say our V vector, if I pick it up and put it here, oh, it's screwed up, okay. That V vector, if I do a multiple of it, it's still on the line, correct? That's the whole idea. Sort of like slope. If I do a multiple slope, it'll tell me where I end up. How many steps up, how many steps over. So, to kind of write this a little differently. R minus R naught. What did we just say is true about it? R minus R naught. R minus R naught must be a multiple of the direction vector. Because I'm on my line, yes? So it must be, let's use T. Why? Because that's what we use. A multiple of my direction vector. Okay. Just like y minus y naught is the multiple of my direction vector. My slope in that case, yes? So the way you normally see this written is like this, and then it really looks like y equals b plus mx if I do it like that. Let me zoom out a bit. Y is starting point plus direction times steps. R is starting point plus direction times steps.
That's all vectors instead of being just numbers.
Exactly. Okay, maybe. No, nowhere near as bad as you might thought it was going to be. So let's write the components of this out. Real quick, R0 is x0, y0. So that's my initial point that's given me. R is just the general point of that's on the line. And V, what we normally do with V is we just call it ABC. ABC are called my direction numbers. And again, reference my earlier note about math people being very creative. They're numbers in the thing that tells me what way to go, so I'm going to call them direction numbers. So how would this look in parametric form? So let's write this out like in full vector form. First off, this will be x y z equals x naught y naught z naught plus t times a b c. Yes. Can you look at just the first components? Can you write an equation with just x stuff in it? Just the first components. How do I get this component? I take this component and I add TA. Good, keep going. To get the y component, I take this component and I add t times b. And I add a component, I take this component and I add t times c. That's crazy. Not surprisingly, does anyone know what we call those? What does T remind you of? What kind of equations that you guys have done before? Starts with a P? Parametric. So these are the parametric. This is the parametric equation form of a line. This, remarkably enough, this here, sorry, is the vector form. That's insane. This is the parametric form. And then, what did you guys remember when you did parametric equations? What was one big thing you did? You didn't like the T, you didn't like the look of it, so you wanted to go in, you wanted to kill it. Yes? You want to say, get out of here, T. Can I eliminate the T? And I don't mean just erase it and hope. Yeah, well, sort of. If I solve the first one for t, what do I get? Yeah, so let me take this away. If I solve the second one for t, it's going to be equal to this because they're both t, correct? If I solve the second one for t, it will be equal to this because this is t, yes? So then I can just keep going. That is called the symmetric equations of a line. So if I know my direction vector, and I know a point my line goes through, I can write it in any of those forms pretty easily. Maybe. This is trippy because, now real quick, I want to show you one thing. If I forced z to be z naught, I forced z to stay z naught, which means I'm not letting my line go up or down. I really want you with me. If I force z to be z naught, my line is stuck here, yes? What am I ending up with if I force z to be z naught? I get this equals that. Do you see how b, I can pull a b up, b over a times the difference in x's, isn't that the stupid y minus y1 equals m times x minus x1, yes? Oh yeah. So you can do that for every plane. You get a line in each plane, yes? Okay, maybe. If you force one to be constant, you just end up with the line in the plane. Okay, maybe. But this one, of course, can go in all three directions. Good. Okay. One little thing that comes up, if I just want a line segment from R naught to R1, let's say. They give me 2 points and they just want a line segment between the two. It would just be, and if you have any experience with general parametric equations, and this would be t goes from 0 to 1. If t is 0, this is just R naught, yes? If t is 1, it's just R1. If t is something in between, you end up with something between those two. So you just get that piece of the line that starts at R0 and goes to R1. That line segment. That might show up in a couple homework problems. It's not a huge deal, but you can just write that down and use it in those homework problems. In the waning seconds of this class, let me just say where we're about to get into. And let me just say this also. I think I'm going to make this official next time, but I'm pretty sure I'm probably going to push the next test. I think it's currently up for the 3rd.
Yes.
I'm almost definitely going to have to push that back a day to March 5th. But anyway, let me know if that's a huge... I don't like to change dates of tests, but just not quite where I want to be, so we can change that. I'll make it official next time. Where we're about to go is we're going to get into planes. And could everybody real quick do this for me? If you're in my linear, you did this already. Can everybody take your writing utensil and just put it perpendicular to your desk? Okay, so all the vectors that are perpendicular to your writing utensil vector, where do they live? In the desk plane, yes? So what's interesting is how many planes are perpendicular to this vector? This one is, yes? This one is, this one is, this one is, this one is. If I gave you this, it's got to be perpendicular to this. If I just told you that eliminates this vector, for example. It eliminates that vector, it eliminates this vector over there, that. I have eliminated a bunch of vectors, but I still have an infinite number. And I also told you a point that's on the plane. Don't those two pieces of information completely determine the plane? If I tell you a vector my plane is perpendicular to, and a point that's in my plane, that's just one plane that completely determines the plane. So that fact is how we develop the formula for a plane. The equation for it. Okay, that's what we'll get into next. So next time I'll have the quizzes graded, whatever homework you've given me. Monday's a holiday. Enjoy it. Have a really nice long weekend. Do a little math in there, thank you.